Hi there, and welcome to another lesson. In this one, we're still doing mass and mole calculations, but what we are going to do is just look at an example from an exam question, and from it, I just want to teach a few additional concepts. Okay, so let's see what they tell us. They tell us to study the following reaction equation. Okay, we can see we have aluminium sulfide, okay, but the correct name, let's even practice a little bit the names. This is dialuminium trisulfide plus 6 H2O. We can just call that water, or dihydrogen oxide, okay, and then this is hydroxide. Okay, so this is aluminium trihydroxide, because there's 3 of them, plus 3 H2 is dihydrogen sulfide. Okay, so let's go and have a look at what they are telling us about this. One thing that I just want you to notice that this equation is already balanced. It already has the coefficients, but that is one of the most important things to do when we're working with mass and moles and a reaction equation. We have to have our calculation balanced. Okay, so let's write important things down. We have to have our reaction equation balanced. Okay, they tell us that 28 grams of dialuminium trisulfide reacts with 17 grams of water. The first thing they ask us is to define moles. Okay, so you could say a mole is 6,0221417 times 10 to the power of 23 number of molecules or atoms. Okay, or if you don't remember that, it should be on your information sheet. You could say is an Avogadro constant. Avogadro constant instead of that number of molecules or atoms. Okay, which reactant is the limiting reactant? Okay, now this is what I would like to highlight, that in a reaction you can see in this reaction that they tell us that once it's balanced, what you need to understand is that the coefficients of this reaction, so there's a coefficient of 1, this is the 3, that tells us in what ratio will this reaction happen. Okay, so you could think of it as moles. For every 1 mole of dialuminium trisulfide, I need 6 moles of water. Okay, because for every 1 molecule of these, I need 6 molecules of these. And for 1 molecule of these and 6 molecules, will produce 6 aluminium hydroxide and 3 dihydrogen sulfide substances, okay, or molecules. Okay, so if an Avogadro constant just represents a number of those, that would mean if I have 1 Avogadro constant of these, I will need 6 Avogadro constants of these, and it will produce 1 Avogadro constant of these and 3 Avogadro constants of those. Okay, I haven't mentioned this before, but you'll notice here in brackets there are some additional information. This just tells you in what state the compound is. For example, we have a solid dissolved into a liquid, and that causes a reaction that produces a solid, okay, and it produces a gas. Okay, so you can imagine dialuminium trisulfide being stirred into water, and that produces a different element at the bottom of the water, okay, and a gas escaping, almost like a effervescent tablet in water, gas escaping from the top through little bubbles. Okay, you can think of it like that. And now the question is, which one will be used up first? If I have 28 grams of dialuminium trisulfide and I've got 17 grams of water, okay, which one will be used up first? The 28 grams of aluminium and I'll have some water left, or will the water be used up and I'll have some aluminium left? That is the limiting reactant. Okay, so if I want to work out the limiting reactant, I need to go and see which one will I have in excess. I need, for every one of these, I need 6 moles of these. So what is the relationship between 28 grams of dialuminium trisulfide and 17 grams of water? Okay, so let's do. In order to do that, we need to find out how many moles of this one do I have and how many moles of that one do I have. If I have 1 mole of this one, I need 6 of that one. If I have more than 1, I need more than 6. We'll look at the exact relationship just now. Okay, so we need the moles of dialuminium trisulfide, okay, which means I'm going to have 2 aluminiums plus 3 sulfides. Let's see what that should be. Okay, aluminium is 27, sulfide is 32. So 2, 27, 3, 32. That gives me 54 plus 96. It gives me a lovely 150 grams. Okay, so if I had 1 mole of dialuminium trisulfide, I will have 150 grams of it. Okay, I have less than that. Okay, so let's work out how many moles do I have. Well, I've got 150 grams. Sorry, I have 28 grams, and for every 150 grams I will have 1 mole. So if we calculate that, I've got 28 divided by 150 gives me 0.1867. So let's keep 0.1867 moles. Okay, now let's see how many moles of water do I have. So if I work out how many moles of water, actually let's see, if I have, before I go there, if I have this many moles, how much water do I need? How much water do I need? Okay, again, look at the ratio. For every 1 mole, I need 6 moles of water, which means I need to multiply. What do I need? I need to take whatever moles I have here and multiply that with. So I need 6 times 0.1867 mole. So I can just take my previous answer and times by 6, okay, giving me 1.12 moles of water. So I need 1.12 mole of water. Okay, so now I have to go and calculate the mole of water. If I have more than this, if I've got more than enough water, then this is the limiting reactant because I have more water. Okay, I'll have an excess of water. If I have less than this amount of water, then water is the limiting reactant. So it is limiting me in producing more because it gets used up. So how much water do we have? Okay, if I calculate it, first I need to calculate the molecular mass for water. I already know molecular mass for water is 18. It's 2 times 1 plus 16. So it's 18. If you do enough of these calculations, you'll quickly remember a few of them as well. Okay, how much mole is 17 grams, okay, 17 grams of water. Now we can, hopefully you can immediately see, oh, I've got less than 1 mole. I need 18 moles to make up 1 mole. Okay, so 17 divided by 18, 17 divided by 18 gives me 0.49. This is how much I have if I, and this is how much I need if I want all of my dialuminium trisulfide to be used up. Okay, so it is clear that water is going to limit me. All of this water will be used up, and I will still have a little bit of dialuminium trisulfide left that would not have any water to react with. Okay, so that would be our answer. Which of the reactants show our all calculations? These are all our calculations. Which is the limiting one? It is water. Calculate the mass of calculate the mass of hydrogen sulfide that is supposed to form. Okay, so what you'll notice in your balanced equation is the coefficient of 3. Now please beware, this doesn't mean we are producing 3 moles of dihydrogen sulfide. It means that the ratio is 3 compared to the other things. So for example, we are making 3 times as much dihydrogen sulfide as dialuminium trisulfide because it is only 1. We are making, if I compare it to water, water has 6, I'm only making 3, which means I'm making half as much dihydrogen sulfide as water being used. So it is very important to know that my products are dependent on the amount of the limiting agent that is being used up. So I can't compare the coefficient with anyone else as the limiting agent. I could compare it with dialuminium trisulfide if I knew how much of that is being used, but I know the dialuminium trisulfide is in excess, so all of this is not being used up. Okay, but I know that all of the water is being used up. For every 6 units we produce 3 units of dihydrogen sulfide. So I know half of the gas or half of the number of moles used in the reactants, that is the number of dihydrogen sulfide produced. Okay, so the number of moles that is being used of water being used is 0.94. So the moles of dihydrogen sulfide is half of that. Half of 0.94 is 47. So this is the number of moles that is produced. And so now I'm just going to work out what is the mass. That's what they're asking me, isn't it? Asking calculate the mass of H2S. So I need, again, I want to calculate lowercase m. I need capital M, which H2S, we know it's 2 hydrogens plus 1 sulfide. Okay, sulfide is atomic mass of 32. Okay, so we have an atomic mass of 32, and so this is a total of 34 grams. Okay, lowercase m is equal to, if you take this formula, n is equal to lowercase m over capital M. You can multiply both sides with a capital M to get a formula for mass as well. So mass is moles times molecular mass, okay, which in this case is 0.47 times 34, and that gives me, Okay, this was what I had before. If I divide this by 2 and I multiply the whole thing by 34, I get a total of 16.06 16.06 grams. That is the amount of the product that is being formed, H2S. Okay, finally, if only 14.28 grams of H2S forms, calculate the percentage impurity of the aluminium trisulfide. Okay, now this question at first glance is somewhat intimidating because you might not understand what they're asking. First of all, what do they mean by percentage impurity? Well, impurity refers to the opposite of pure. Okay, so if I had purely products in the end I only have products. In other words, I've got only aluminium hydroxide and only dihydrogen sulfide, then I would have a pure reactants in the end. But as it stands, if I only have if only 14.28 grams of H2S forms, it is clear that this reaction has not fully completed, because it would be completed if this much mass is produced. Okay, and we can see that 16.06, we can see only 14.28 grams is produced. So the question is, the percentage impurity of dialuminium trisulfide would refer to the after the reaction, okay, the mass of dialuminium trisulfide. It's basically what I'm trying to calculate. Dialuminium trisulfide divided by all of the other substances masses. Okay, so will there be water left? Yes. So it will be the mass of, let me do it like this, the total mass. The total mass. Okay, so let's go ahead and do that. Now I must be honest that I think this question is somewhat ambiguous, because we are not sure with the information given whether this gas is escaping. Okay, because if this gas is escaping, then obviously the total mass in the end is not the same as the mass in the beginning, and all the mass that escaped we must subtract from the reactant. So we can maybe look at both cases. But if it is a closed system, and this brings me to the final thing I want to highlight in with this question, is the principle of conservation of mass. Okay, that principle says in a closed system, the mass before the reaction occurs, the mass, let's put it, the mass, before a reaction occurs must be equal to the mass after. Okay, now actually you can think of it like that, or you can simply think of it in the sense of, if I have a closed system. A closed system just means none of the reactants or the products can escape from wherever I'm doing my experiment, okay, or wherever this reaction is occurring. That's a closed system. Nothing can escape from this system. Even gases are kept inside. So in a closed system, the mass before the reaction occurs must be equal to the mass after the reaction occurs. So basically it means that at any point, if you were to put this whatever closed system you have, if you were to weigh it consistently, if you to get the mass consistently, you will always see the same value, no matter what is happening inside, as long as nothing is allowed to escape. Okay, so that is the principle of conservation, which means if we wanted to work out the total impurity of dialuminium trisulfide, it means we're trying to work out the percentage of the reactant still in the solution after the reaction occurs. And after the reaction occurs, we have to take the amount that we still have divided by the total mass to find the percentage of dialuminium trisulfide still in the solution. So total mass, if I could assume that nothing could escape, the total mass would be equal to the total mass in the end would be equal to the total mass in the beginning, which I have. My product in the beginning was 28 grams of dialuminium trisulfide and 17 grams of water. So I can start with that. I've got 28 plus 17, and that gives me a total of 45. 45 grams is my total. Now all I need to know is how much dialuminium trisulfide do I have left. Okay, well, it works very similar to what we had before. We can see that for every 3 moles of dihydrogen sulfide, we will get 1 mole of, or we need to use up 1 mole of dialuminium trisulfide. So the ratio is 1 to 3. But again, I can't look at the mass to determine this ratio. I must look at the moles. Okay, so I need to work out how many moles are there, how many moles of H2S has been produced. Okay, so let's see. The atomic mass of H2S we calculated as 34. Okay, so how many moles of that is in 14.28, I think. 14.28 grams. 14,28 grams divided by capital M gives me 14.28 divided by 34 gives me 0.42. 0.42. Now the ratio, again, here, the ratio is that 3 of these will be produced for every 1 of these produced, which means that H2S is 3 times more than dialuminium trisulfide, which means to get dialuminium trisulfide of dialuminium trisulfide, I still need to take this value and divide it with 3, because this one will produce 3 times as much as we used for that one. Okay, so if I divide it with 3, I get 3 goes into there 14 times, so 0.14 moles of this is still in among the products that was produced. Now again, I can't work with this when it comes to the actual percentage, because in my percentage question I need to work out the amount of grams that are left. Okay, so to work out the mass, I would use the number of moles times the molecular mass. Number of moles I see that still exist. Sorry, I mean the number of moles that reacted. Sorry, I misspoke. The number of moles that reacted during this reaction is 0.14. Okay, this is not there anymore. How much mass is not in dialuminium trisulfide anymore? Dialuminium trisulfide, calculated before, so let's go back there. That is 150 grams. So 150 grams gives me, okay, 0.14 times 150 grams is equal, I made a mistake, 0.14 times 150 is equal to 21. So 21 grams was used. Okay, again, 21 grams was used, which means of my 28 grams, I still have 7 grams of impurity. 7 grams has still not been used up. Okay, so of all of the reactants, okay, or all of the mass, 7 grams of that mass is still dialuminium trisulfide, which means it is the impurity in the product. It's still reactants, that's why it's impurity. Okay, and if we work that out, what percentage? 7 of 45 grams is equal to 0.1556. I go to 4 decimal places because percentage we want to round to 2 decimal places and multiply by 100. So okay, there we go. 15.56 is still impurity. I just want to break this down a little bit further to explain to you how exam questions are weighted in an exam. This is typically an example of a knowledge question. That's typically level 1 questions. Okay, which reactant is a limiting agent? This is typically a level 2 question. It's a very basic standard application. Calculate the amount of mass of H2S that is supposed to form. Okay, this is borderline level 2, level 3 questions, but it just involves thinking maybe 2 steps ahead. And this final one is typically a level 4 question where you have to show insight into what is happening here, what is an impurity. It involves more than 2 or 3 steps in your calculations, and that's typically called level 4 questions. So this is a very instructive exam type question. It uses a lot of this, and in general this is a topic that students have difficulty with. I do hope your understanding of this was sufficient and that you were able to do questions like this in the future. Good luck, and I hope you enjoy it.